Yeah, so thank you so much for including this paper in the program, the conference. I'm Jun at HKUST. I wish I could participate in a conference in person, but unfortunately, I'm not in Hong Kong now. And this is a joint work with my friend at UC Berkeley. And I'm very happy that I can share our new research on this automated market makers. Okay. Here is a little bit of background. So traditionally, for example, like if you want to trade cryptocurrencies like Bitcoin or maybe Ethereum, I guess the most common way is to use this centralized exchange platform like Binance, Clarken, or maybe Coinbase, Bittrex. Right? We have many this kind of famous exchange platforms. And they are called centralized exchange because we have just a single centralized authority who controls the exchange platform. Right? For example, like if you want to trade on Binance, you have to say transfer your money from your bank account to Binance account. So Binance has custody of your fund. Okay? And of course, if there is some trouble, maybe the cybersecurity attacks, then it is possible that you're going to lose your money. And also, like if Binance central system got some trouble, then it is possible that transaction will be suspended. Okay. And all these kind of problems can happen because we have just a single centralized authority, which is Binance. Okay. So that's why they call centralized exchange. And in order to overcome this kind of problems, I guess a natural idea is to bring this kind of system to the blockchain, distributed ledger system. And we have many exchange platforms built on the smart contract of Ethereum blockchain, and they are called decentralized exchange platforms. Okay, because it's all distributed, decentralized, and there is no such kind of centralized authority who controls the exchange. And of course, they are quite different. I mean, the decentralized exchange, centralized exchange, they are quite different in many aspects, like custody of your funds or requirements of the know your customer information, or with the trade execution or order matching. Those are quite different. But in this paper, we are going to focus on the difference in pricing algorithm, okay, or with like a market microstructure engine. So on a traditional centralized exchange platforms, we know that we typically use this limit order system, right? So if you go to Binance trading platform, you will see this kind of screen, which is of course the limit order book, right? So you have to deal with this kind of screen with limit orders, market orders, or sometimes more kind of sophisticated orders, okay? And traders will be trading with each other, and price will be determined as the, by the proposed bid and ask quote. But this kind of limit order system is quite complicated. It's quite complicated matching algorithm. And also you have to deal with this kind of huge information. So it's not really feasible on the blockchain environment because the blockchain has only a limited capacity, and you have to pay this kind of miner fees, okay, which is expensive. So instead of using this limit order system, many decentralized exchange platforms are using this automated market makers. Okay. So this is kind of new market making algorithm or market structure. Okay, which is quite simple. It's kind of, you can think of it as the predetermined single pricing equation. And before I explain what this automated market makers are doing, let me show you this figure. Okay, so this is a trading volume on a decentralized exchange platforms, which is, as you can see, it's growing a lot. And here I also decompose trading volume on a decentralized exchange with automated market makers, this red one, from those on a DX with order book system, this blue one, right? And I think it's quite safe to say that this kind of recent growth on a decentralized, in a decentralized exchange platforms is mostly driven by the automated market makers. Okay, so automated market makers are playing a very important role in the prosperity of DX. Okay, but remember, this is a comparison between DX with AMM and DX with limit order system. What about the centralized exchange? We know that still centralized exchange platforms with traditional limit order system, they're trading a lot. They handle huge trading volume like a Binance, FTX, Clarkham, Bittrex, they're trading a lot. So in a real financial market, they coexist. So this kind of new decentralized automated market and the traditional centralized limit order market, they coexist. Of course, we don't know which one is going to dominate in the future, but at least in the transition, we have both. Okay. So we want to know what's going to happen if we have both of this kind of new one and old market making structure. So we provide a theoretical framework to analyze this kind of situation. And because it is a finance paper, we introduce asymmetric information problem, like some trader knows material information while other traders don't know. Traders' platform choice is also endogenous, and liquidity on both types of platforms, DX and CX, liquidity will be endogenously and jointly determined. So we can analyze how they interact with each other. So this is what we are doing in this paper. Okay, and I think it's appropriate time to talk about this, briefly talk about this automated market makers. So how they determine the price? And so as I said, you can think of it as the pricing functions. And depending on the functional forms, we have several categories of automated market makers. And the simplest, and I guess the most widely adopted design is this constant product market makers. Okay, suppose that the exchange or automated market or DX is trading cash and some token X. Okay, of course, it could be token versus token transaction, but in order to make it kind of easy to digest, let me talk about cash versus token. And to begin with, liquidity provider is going to inject both token and cash into the exchange. Okay, let's say X0 unit and C0 unit, token and cash. Then the automated market is going to aggregate this kind of provided asset and generate reserve of asset and cash, which we call liquidity pools. Okay. And given this kind of initial liquidity pools, we can pin down some constant as the product of this X and C, because this is a constant product market. And by using this equation, of course, we can draw this kind of convex curve, which we call the bonding curve. And all transaction must be on this curve, or conducted on this curve. So what does it mean? Suppose that there's a liquidity taker arriving at the market saying that I want to buy delta X unit of token X by paying some cash, right? Then this guy is going to withdraw delta X unit of token X from this X liquidity pool. But of course, this guy must pay cash. So he's going to add cash to the cash pool. Initially, we were here, but after the trade, the state of the liquidity pools will be somewhere around here. But as I said, automated market makers require that even after the trade, liquidity pools must be on this curve. Okay. And this is going to determine the price because we got this single equation. So before the trade, we had this product. While after the trade, the product is this one, right? And because this is a constant product market makers, they must be constant. So we got this single equation, and of course we can solve this equation for the amount of cash this guy must pay, like delta C. And if you divide it by delta X, of course it's going to be the price for this trade. It's quite simple. So it's quite simple, and I guess it's quite different from the limit order system, because on the limit order system, as I said, traders are going to be trading with each other, and the price will be determined by, bid and ask quote by the market makers. But here on the automated market, traders will be trading on trading against liquidity pools, and the price will be automatically determined by this kind of pre-specified algorithm, a pre-specified function. Okay. So they're quite different, but as I said, they coexist. So we want to know what's going to happen. Of course, we have several papers on automated market makers or decentralized exchange in general, but the point is they assume that there is some exogenous centralized exchange. Okay? Or maybe the central question is, how the asset price on a decentralized exchange converges to the reference price on a CX, but the reference price on a CX is exogenously given. And at the same time, traders have no choice in their trading platform decision. Okay. But yesterday, one of the paper by Zhou and also Shiyang is going to discuss on my paper. Their paper is empirical study on how prices on these two types of platforms interact with each other. Okay, and we provide a theory. Of course, the focus is a little bit different because their paper is more like about the like a trust and regulation, but our paper is more about the kind of market microstructure difference. Okay, so here is the key, the summary of the key findings. So in the first part of the paper, we analyze how traders will, endogenously decide on their trading platforms, reacting to some exogenous variations in a DX liquidity. Okay, so here, DX liquidity is exogenous. And we find that it depends on your informational background. Okay, so depending on whether or not you're informed or uninformed, your preferred trading platform will be different. Okay, so informed traders and noise traders, they will exhibit kind of different reaction to the exogenous fluctuations of DX liquidity. Okay. And because of that, of course, the signal to noise ratio, or maybe the adverse selection problem for CX market maker will change, and bid-ask spread will be also affected by liquidity on a DX. Okay, or more precisely, we find that DX liquidity will have positive impact on CX liquidity. So this first point is actually the comparison between informed and uninformed guys. But even if you look at, or maybe the focus on informed trader, they will exhibit different reaction depending on whether or not you're buying or selling because of this kind of convex pricing. I will show you later. And because of that, we can find that buy order and sell order will exhibit kind of asymmetric informativeness. Right? So observing buy order and sell order, the precision of your prediction will be different. And also because of that, bid and ask prices will be asymmetrically distributed around the not the midpoint, expected value of the asset. There's sort of the kind of empirical prediction of our theoretical model. In the second part, we endogenize DX liquidity or DX liquidity and CX liquidity together. And we conduct some comparative statistics. And I guess one of the interesting results here is that we find that DX liquidity or supply, the DX liquidity will exhibit ambiguous reaction to the volatility of the asset. And this is kind of new because all existing studies suggest that DX liquidity always negatively reacts to the asset volatility. Okay, but in our model, it depends on parameter value. Okay, so here's a model. It's quite simple. We're just going to have one asset whose common value is equal to 1. Okay, so again, we're going to think about cash versus asset trading, but you can also think about asset versus asset or token versus token, in which case the value is just a relative value and the price will be just the exchange rate. Okay. In a first period, market maker is going to supply liquidity, both on a centralized limit order market and a decentralized automated market. Okay, we're going to have competitively many market makers on both exchange. In the second period, there is some shock, triggering some liquidity taking orders. Right? So with probability eta, the shock is going to hit the common value of the asset. And in this case, the shock is going to increase or decrease the asset's value by sigma with the same probability. Okay. So you can think of this sigma as the volatility of the asset. In these cases, there are some traders who know the realized value of the shock, and in order to make some positive profit, they're going to trade. Okay, so there are some informed traders. With the complementary probability 1 minus eta, the shock is not going to hit the common value of the asset, but it's going to hit the private value of trading for some noise traders. So they are sort of the exogenous guys trading because of some non-fundamental reasons like hedging motifs, margin constraints, or some other like a borrowing or lending requirements. Okay, so they're randomly buying and selling. So we're gonna have informed trading and noise trading. And this is not really important, but in the last period, the information will be public and the price will be adjusted, either because of the market makers repricing or additional arbitrage trading. But it's not really important. This is just to make the model consistent with the real market. So the important thing is market makers liquidity provision and informed and noise traders behavior. Informed traders, they're gonna align with probability eta, and depending on the sign of the shock, they're gonna be buying or selling one unit. And upon arriving at the market, they're going to compare the marginal trading cost, these platforms, okay, CX and DX. And if the shock is positive, we denote the fraction of informed traders buying on a DX by this beta bond, right? And similarly, beta sell shows the fraction of the informed traders selling on the decentralized exchange. And they could be different. Beta buy and beta sell could be different because of this kind of asymmetric buy and sell price impact on the DX, which I will show you later. Noise traders, they are randomly buying and selling some exogenous units. And I gave them some private utility from trading, as well as some heterogeneous preference for DX and CX, okay? So it could be, for example, like, we know that the decentralized exchange is a little bit slower compared to the centralized exchange because of this kind of mining process. Or maybe we know that the centralized exchange is kind of riskier in terms of this kind of cybersecurity risk, okay? And this kind of sort of the preference for CX and DX will be summarized by this kind of heterogeneous exogenous preference for noise trading. And we assume that noise traders are going to decide on their trading platform before they enter the market, okay? And alpha fraction will be trading on a DX. But this could be actually relaxed while the analytical solution will no longer be available. Right. So here is kind of illustration. So informed traders, noise traders, they're going to be endogenously differentiated between these two platforms. And on the centralized exchange, we apply traditional sort of the Grossman-Milgram type argument. So the competitively many market makers going to propose break-even bid and ask prices. And from the literature, we know that bid and ask prices will be dependent on the signal to noise ratio or adverse selection cost, or I should say how many informed traders will be trading compared to the noise traders. The question is, what would be the price on the automated market? So as I said, in the first period, the market maker is going to inject both asset and cash into the decentralized exchange, decentralized automated market. And here, let's assume that X0 unit of assets are provided. Okay, so here this is exogenous, but as I said, it's going to be endogenous in the later section. And once you decide on how much asset you're going to provide, the automated market maker is going to, pin down the amount of cash you have to provide. Okay, so you're going to inject this X0 and C0, but liquidity supply will be characterized by this X0. Then, why do you want to supply liquidity? Of course, there's some return, or maybe cost. So there are two sources of return. One is the changes in the state of the liquidity pool, and the second one is the trade execution fee. Okay. For example, like you were initially here when you supply liquidity, but because of the trade, it's going to go up or go down, and the difference between this one could be your payoff. Okay. And you can also get the trade execution fee as your profit. What about the price? So in this model, we assume that the price will be determined by this general automated market making function, which is given by some function f. Okay. So this function is a function of initial state of the, initially we're gonna have this kind of liquidity pools. And after the trade, we will have these liquidity pools. And some function of these liquidity pools must be constant before and after the trade. Okay. And we are not gonna specify, we're not gonna provide a specific functional form of this F in order to make the discussion as general as possible. But for example, if you want to talk about CPMM that I showed you, you can just assume that function is just a product. Okay. And the assumption we're going to impose for on this F is that this bonding curve must be convex, okay, like this one. And this is, I think, a very natural assumption, given that almost all automated market makers in a real financial market satisfy this condition. Okay. And if you play with this kind of functional, this kind of pricing function, we find that marginal price on a decentralized exchange is an increasing and convex function of the trading size. It is a decreasing function of the size of the liquidity provided, only if you're buying. Or if you're selling, it's going to be an increasing function of the liquidity pool size. And the last important property of this marginal price is that price impact is the decreasing function of the liquidity pool size. Okay, so the larger the liquidity pool, the weaker price impact you're going to incur. So we can think of this X0 as the measure of the liquidity in this market. All right, so I already showed this price. Okay, so now we pin down the bid-ask prices as well as the marginal prices on the decentralized automated market. It depends on the trading size, initial liquidity, as well as you have to pay some trade execution fees. Right. And if you solve the indifference conditions for informed traders and noise traders, you can pin down sort of the unique and stable solution. Okay, so we can pin down unique equilibrium measure of informed traders trading on a DX, as well as the measure of noise traders trading on a DX. They are functions of initial liquidity. So first, given this initial liquidity, how do they decide on their trading platform? First, we know that we find that informed traders, they are concerned about DX liquidity. Why? So basically, the informed traders, they tend to cluster on the same side of the market because they are trading on the same information, right? If you got the positive news, then all informed traders will be buying on the market. And of course, this is going to generate a large shift in the liquidity pool, and each informed trader tends to incur relatively large price impact. So that's why they're concerned about X0. But this is not true for noise traders because noise traders, they are random traders. So they know that random buy and random sell order tend to cancel out. And liquidity pool will not change that much. So each noise trader incur only a limited price impact. So that's why they're not concerned about X0. Okay. So they're different. And as a consequence, we have this kind of result. Suppose that DX liquidity improves, say exogenously improves. Then, as I said, this is going to reduce the price impact. And informed traders, they are very happy about it because they can enjoy this reduction in the price impact. Okay. But in contrast, noise traders, they don't react that much because they face the limited price impact to begin with. And because of that, informed traders, they want to migrate away from centralized exchange to the decentralized exchange. And this is going to, of course, improve the adverse selection problem on a centralized exchange. So the bid-ask spread shrinks and centralized exchange becomes kind of cheaper for noise traders. So the noise traders is going to migrate to the centralized exchange. And as a result, the adverse selection cost for CX market maker is going to improve even more, and bid-ask spread shrinks even a lot. So that's why we can conclude that DX liquidity is going to have positive impact on a CX liquidity, or should say negative impact on the bid-ask spread on a CX. Okay. And this result is going to be very useful, maybe helpful when you endogenize DX liquidity. So in order to endogenize DX liquidity, we have to pin down the profit function for DX market makers. Okay? And this is quite similar to the traditional sort of the limit order adverse selection discussion. Okay? So the market maker's profit or maybe cost comes from the informed trading and noise trading. If the trade is initiated by this informed trading, market maker is going to lose money because informed traders always withdraw more variable asset by adding less variable asset to the liquidity pools based on their information. So whenever informed trading happens, the value of the liquidity pool always declines and the market maker is going to lose money, right? So in this kind of DeFi field, this is called impermanent loss, but essentially this is same as the adverse selection cost. In contrast, if noise trading happens, they're random trading. So the state of the liquidity pools will not change in expectation, but they're going to pay trade execution fees, generating positive profit for market maker. So the profit function for the DX market maker is going to have this negative component because of the informed trading adverse selection, and a positive component because of the noise trading and the execution fees. And if you combine this functional form and the previous result, it is easy to see that this is a decreasing function of the total liquidity supply. Because if you have kind of larger liquidity pools, we know that informed traders, they're more likely to trade on a DX, while noise trader, they tend to avoid decentralized exchange. This is a previous result, right? So the profit component declines, or maybe the shrinks, while the cost gets larger. So that's why profit function is decreasing function of X0, and we're going to have this unique and stable equilibrium liquidity supply. And so by using this X0 star, which is the sort of the endogenous DX liquidity, we did some comparative studies. And as I said, I guess the one of the interesting result is this kind of reaction of the equilibrium variables to the assets volatility. So here, I think we should focus on this first panel, where I plot the equilibrium supply of the DX liquidity and its reaction to the asset volatility, sigma. It's hump-shaped. Reaction is ambiguous. And here I changed the value of eta, which is the frequency of the informed trading. We find that this ambiguous reaction is quite robust. For example, even if you change the value of the other parameters like Z, which is the noise traders trading volume, we still have this kind of ambiguous reaction. And as I said, this is kind of novel because the existing papers all suggest that X0 star, or maybe the equilibrium supply of DX liquidity, should be always decreasing function of the asset volatility. So why we have this kind of different result? So first of all, suppose that the asset becomes more volatile, sigma goes up. On a decentralized exchange, this is going to increase the size of the impermanent loss. What should you say, like the adverse selection problem becomes worse. And the market maker's profit declines, so each market maker gets reluctant to supply liquidity. So that's why this X0 star is a decreasing function of sigma. But in our model, we have this second competing effect. On a centralized exchange, we know that the bid-ask spread gets wider exogenously due to this volatile asset. Then both noise traders and informed traders want to avoid centralized exchange and want to migrate to the decentralized exchange because CX gets kind of more expensive. But informed traders, they are concerned about clustering on a decentralized exchange, while noise traders, they don't care. So it's easier for noise traders to move to decentralized exchange compared to informed traders, right? And because of that, market makers on a decentralized exchange face the kind of more profitable trading opportunity and more willing to supply liquidity. So we have two competing effects. And obviously, this second effect is kind of novel and unique to our model of coexisting. endogenous two exchange platforms with endogenous platform choice. Because for example, like if the CX price is exogenously given, we don't have this statement. Or if the platform choice is also exogenous, we don't have these three-step arguments. So that's why in the existing model, we only have this first one, while if you add this kind of generalized model, you will have this second competing effect, as well as this ambiguous hump shift reaction. Because I'm running out of time, I will just briefly mention this additional result. So because of this kind of convex curve, liquidity withdrawal and liquidity addition is going to incur asymmetric price impact. And because of that, buyers and seller will exhibit also asymmetric reaction. And because of that, informativeness of the buy order and sell order will be asymmetric, as well as the bid-ask midpoint will be biased toward upward. Okay, so there are sort of the testable implication, because if you think about kind of new listing of kind of new token pairs, and if you compare the bid-ask spread on a centralized exchange with the same pair, then you will test this kind of result, I guess. Right. So decentralized exchange proposes a new market making structure, and we analyze what's going to happen if this new market making and a traditional market making coexist. Okay, so this is a conclusion, and yeah, that's it. Thanks so much for listening to my presentation.
All right, thanks to Jun for the very interesting talk and perfect timing. So the discussant is Shiyang Huang from the University of Hong Kong.
Okay, let me share my screen. Okay, you see my screen now?
Yeah, can you full screen it? Okay, great. Yeah, looks good.
Okay, thanks a lot for inviting me to discuss this interesting paper. This paper is quite trendy, and this paper is talking about important topic. And this paper also fits my recent research interest. As mentioned by John, and my co-author just presented our empirical DP finance paper yesterday. Okay. Now, before I talk about my comments, let me quickly summarize this paper. In this paper, the author just proposed a theoretical framework to analyze the effect of decentralized automatic market making on the traditional centralized limit order market. And there are several important model features. First, as most market structure models, there are three types of players: informed investor, and liquidity trader, and liquidity providers. Okay. And there are two trading exchanges. One is a centralized limit order market. The other one is decentralized exchange. And this decentralized exchange is with automated market making. And the centralized exchange is a limited order market. Liquidity provider set the bid and ask price. This is what we know. And as we know, the bid and ask price are determined by the probability and of informed orders relative to the liquidity traders. And the decentralized exchange is quite different. Decentralized exchange has automated market making. So it has a liquidity pool. The price of an asset follow a constant function. For example, if we have two tokens in the liquidity pool, the amount of these two tokens are X and Y. And the constant function is denoted as fxy. Okay, now how to determine the price? And if an investor want to buy delta of token X, so the price should satisfy a constant product of constant function, say fx minus delta x, and y plus p times delta x equals fxy. Okay, and that's one important feature of this pricing rule. So this is when the investor want to buy a larger quantity, the pricing impact or the price she must pay is larger. One example of the pricing function is just a constant product. With the constant product market making, the price just equals y over x minus delta x. As we can see, when delta x is higher, so the price is higher. Okay, it's also quite clear on the figure here. Now, the author take two steps to conduct analysis. In the first step, the author consider a partial equivalent. In this partial equivalent, the liquidity pool of the decentralized exchange is exogenous. And actually, this step is quite important for understand the key intuitions. So the author found several novel and interesting results. For example, the author found the decentralized exchange liquidity has a symmetric impact on the informed buy and informed sales. Actually, this is due to the larger price impact of informed buy and then the informed sell on the decentralized exchange. So this means informed buyer prefer, relative to informed seller, informed buyer prefer centralized exchange to the decentralized exchange. Okay, so this means in the central exchange, so most buy orders are from the inform trader. Okay, and there were several interesting results. For example, when liquidity pool on the decentralized exchange increases, the price impact decreases. This is quite intuitive. And here, inform investors tend to cluster on the decentralized exchange. And when inform investors cluster on the decentralized exchange, so this will make adverse selection problem more severe on the central exchange. So less severe on the decentralized exchange, and the BRSY becomes smaller. So as a result, the liquidity trader will migrate to the central exchange. This is a key intuition for the first step. Now, in the second step, they also consider endogenous liquidity pool of the decentralized exchange. So liquidity provider now need to choose whether to provide liquidity on a centralized or decentralized exchange. So this step is quite complicated and also just rely on numerical exercise have some novel results. For example, when the asset become more volatile, the liquidity on the decentralized exchange decline. So this is quite straightforward. This is due to the more severe adverse selection problem. And the most interesting result is informed seller tend to cluster on the decentralized exchange, and the informed buyer tend to cluster on the central exchange. At the same time, informed trading become more likely to on the decentralized overall. So liquidity provider will tend to migrate to the central exchange. Okay, this is the key summary of the paper. Overall, I like this paper a lot. Given the rise of deep finance, this paper will be an important paper in the literature. And as mentioned by John, this is the first theoretical paper in talking about combination of decentralized and the centralized exchange. And our paper is the first empirical paper on both the centralized and the centralized and decentralized exchange. And also, as I can see, the authors are also very careful to execute the model. For example, also consider several important model extension and also carefully discuss the bias assumptions. But after careful reading and thinking about the model, I also have several comments. I think the paper can be further improved on several perspectives. For example, the more economic interpretation and the discussion of the robustness. Okay, this is my first comment. My first comment is regarding the interpretations. The first interpretation issue is about cryptocurrency fundamentals. So what's the cryptocurrency's fundamental value, or what determines the fundamental value of a cryptocurrency? So actually, I've been thinking about this question for a long time, and this question is quite important. Not surprising, as a early stage financial innovation, cryptocurrency have a larger return volatility. So it's unclear what determines the cryptocurrency's value. So because I do not have a clear answer by myself, I'm very careful in talking about informed investor in my empirical DeFi paper. So it would be great if we also can identify fundamental value of cryptocurrency. So actually, if we also can identify the fundamental value of cryptocurrency or identify the determinant of the fundamental values, they also can just follow literature such as Manqui, Yuesen, Zhu 2017 and test some important implications. The implication can include packing orders or trading value between centralized exchange and the decentralized exchange. Okay. But if we cannot perfectly identify cryptocurrency's value, we need to stand back. For example, it's quite important to interpret informed investor. It's also quite important to tell the reader what do informed investors know about. Do they really know about cryptocurrency value or just the short-term price change? Okay. The second interpretation issue is regarding delay cost of liquidity trader on the decentralized exchange. So they also just follow Zhu 2014 and assume that liquidity trader incur delay cost in trading the in the decentralized exchange. Okay, specifically, the delay cost is just gamma times sigma. Here, gamma is aversion toward the delay, and the sigma is asset volatility. Okay, I totally understand the reason why they also want to have this kind of assumption. So actually, this delay cost is to pin down the endogenous liquidity trader choice between decentralized and central exchange. But however, the economic interpretation is unclear to me. So actually, the motivation for this delay cost is from Zhu 2014. But Zhu 2014 focused on dark pool. In the dark pool, investor may not execute their order immediately. This is true because dark pool is not centralized exchange. We can imagine dark pool is just OTC market, and the buy order need to meet the sell order. But this means the market the order will not be matched immediately. But in this paper, liquidity trader can immediately execute their order on both centralized and the decentralized exchange. So I'm not comfortable about this interpretation of the delay cost in the paper. So more importantly, the author just assume that informed investor on the decentralized exchange have no such a delay cost. Okay, but this is quite different from liquidity traders. But this seems a little bit logically inconsistent to me. As we can see in June 2014, both the liquidity trader and the informed trader have a delay cost in the dark pool. So this makes a lot of sense to me. So I think Jun, you and your also should be very careful in assuming the delay cost. Another issue is related to detailed specification of delay cost. As I point out here, the delay cost is just gamma times sigma. Sigma is asset volatility. But after going through some detail of results, I find that some results are quite sensitive to this specification. Probably we can have a thought experiment. Now we can consider alternative specification of delay cost. Say the delay cost is just gamma. For me, this cost has also some solid interpretations. For example, when liquidity trader have some endowment shock, the endowment shock is just gamma shares of underlying asset. And now the liquidity trader have some inventory cost. This is quite common in the market structure. So as we can, with this alternative specification, so I can solve that. The population of liquidity trader on the decentralized exchange is just 1/2 of the BR spread on the centralized exchange. But this is different from the current model. In the paper, the population of the liquidity trader on the decentralized exchange is just 1/2 of a normalized BR spread. Okay, and then we can see some result may change. For example, as I showed you several minutes ago, the author found that when asset become more volatile, the BR spread becomes larger, and the normalized BR spread decreases. Okay, the liquidity trader on the decentralized exchange decreases. But with this alternative specification, liquidity traders only care about BR spread rather than the normalized BR spread. Now, when the liquidity trader may prefer the decentralized exchange to the central exchange. Okay. Now, given that some results are quite sensitive to the specification of the delay cost, the author should just provide some strong justification for this delay cost, or the author can just discuss how their result are robust to the specification of the delay cost. Okay, this is my first comment. My second comment is about model robustness. The novel result in this paper is that liquidity provision on the decentralized exchange has a symmetric impact on the informed and the informed buy, informed sales. But intention is like the execution probability of in the dark pool of June 2014. Now, this is due to the constant function pricing rule. First, informed investor either buy or sell is always in the same direction. And this means the trading is correlated among informed investors. Now, with the constant function pricing rule, informed buy have a larger price impact than the informed sell. This means population of informed buy is lower than the informed sell on the decentralized exchange. But actually, when we're talking about liquidity trading, it's quite different. In sharp contrast, there's no correlation among trading among liquidity traders. So this assumption is quite crucial. As the liquidity trading is independent across different liquidity traders, so one liquidity traders will not generate large impact, or we can say the expected price impact of liquidity trader is 0 in the decentralized exchange. But after carefully thinking about the model, I find some results are quite sensitive to this assumption. Then we can have another thought experiment. Now we can assume liquidity trader have some common liquidity shocks. So the common liquidity shock can be arising from sentiment or common margin cost. In this sense, liquidity trader also are always traded in the same direction. Okay, now given the lower price impact of sales, liquidity seller are more likely to trade on decentralized exchange than liquidity buyer. Okay, so actually the intention for the informed trading can also be applied to the liquidity tradings when we assume there's a common liquidity trading. So as a result, on the central exchange, buy orders are also more likely to come from liquidity traders. So this is a sharp contrast to the current model. In the current model, buy orders on the central exchange are more likely to come from informed traders. So this intuition can generate result which may totally different from the current model. For example, when buy orders on a central exchange are more likely to come from liquidity traders, the ask price will become lower. Okay. Now when we talk about midpoint of bid ask price, we can see probably the midpoint of bid ask price, it will be lower than the expected value asset values. Okay. But actually, as shown in the corollary 1 of the paper, the midpoint of the bid ask price is higher than expected asset price. In this sense, the central exchange may overvalue the price on the central exchange. This is my second comment. My third comment is regarding some intuition of the main result. Okay, with the endogenous liquidity provision, they also find that when assets become more volatile, informed sellers tend to cross on the central exchange, and the informed buyer tend to cross on the central exchange. So this result is quite interesting, but intuition is not crystal clear to me. First, I can totally understand the intuition for the negative impact on asset volatility on informed buyers on the central exchange. For example, as shown in problem 2, when the liquidity pool on the central is higher, so the price impact is lower. So informed buyer want to cluster more on the central exchange. So this is due to the lower price impact for the larger liquidity pool on the central exchange. But this intuition should also be applied to the information sellers, right? For example, when the liquidity provision on the liquidity pool is higher, probably we expect the information seller also want to trade more on the central exchange. Unfortunately, this is not what we see in the numerical exercise. But of course, for information seller, the information seller want to compare the trading costs on the centralized and centralized exchange. So to have a positive, as I understand, to have a positive association between asset volatility and informed sales on the decentral exchange. So the necessary condition will be the asset volatility will further lower the bid ask. Unfortunately, also do not show this is the case. So I strongly suggest also to explore this possibility. Okay. My last comment is about the optimal design of pricing rule on the decentral exchange. There are several important implications. As we can learn from the model, introducing decentral exchange can improve liquidity on the central exchange. So the bid spread on the central exchange becomes smaller when we introduce decentral exchange. But however, when we're talking about asset classifications, we will find when we introduce decentral exchange, it seems the assets on the central exchange will be overvalued. So this is the midpoint of the bid spread is higher than as a payoff. Okay. So actually, this is due to the constant function pricing rule, right? So with the constant pricing function rule, it will generate a symmetric price impact on the informed buy and informed sales. So actually, informed buyer are more likely to trade on the central exchange than the informed sellers. So the natural question is, can we have an optimal pricing rule which will improve liquidity on the central exchange and just reduce the overvaluation on the central exchange? So actually, there are some alternative pricing rules. For example, we have a constant sum pricing rule. This is also a whole debate on the constant pricing rules. So actually, the constant pricing rules definitely can have a symmetric impact on informed buy and informed sales. So in this sense, with the constant sum pricing rules, probably we do not see overvaluation in the central exchange. But I'm not sure about the implication of the constant sum pricing rule on the centralized exchange's liquidity. But okay, anyway, given such a benefit, I think also could discuss a possible optimal design with the direction of a constant sum. So actually, this is a topic in Gabani's recent paper, right? Okay, let me quickly conclude here. Overall, I think this paper is very interesting. Given the trendy topic of DeFi, I truly believe this paper will be an important step in the literature. Okay, I truly believe that this paper will greatly improve our understanding on how automated market making affect the centralized limit order books. But I think the paper can further improve on the following several perspectives. For example, the author can just discuss more about the model robustness or just justify some standard assumptions such as the delay cost. Okay, Thank you.
Great. Jun, do you want to respond to Shiyang's comments first?
Oh yeah, thank you so much for a great discussion. All points are very important. Also, you show kind of sort of the avenue for further development of the paper. I really appreciate it. Especially like for example, like optimal DX design. This is actually the important topic and something we want to actually address. But the point is, this paper cannot discuss the welfare because everything is it's kind of zero-sum game. So maybe this is a point that we have to kind of modify and so that we can talk about welfare and optimal design. Delay cost. That's actually very critical point. And in the current version, the newest version, latest version, we try to make it more kind of general kind of preference for noise traders. Of course, yeah, as you said, delay cost is super specific and it's quite difficult to specify what is a negative component delay cost or why informed traders are not affected by delay cost. So we try to accommodate this kind of stuff in the current version. And also delay cost proportional to sigma. You're right. So in a latest version, we removed that assumption. Sorry that we couldn't update the latest version with you in the last minute. Yeah, by removing that kind of assumption, we got this kind of hump shade reaction. So I guess your prediction is correct, and that's why we got this kind of sort of the new kind of interesting result. Yeah. More things I want to answer, but I guess we are running out of time, so maybe I should stop here.
Okay, we also have one question from the chat if you want to briefly respond to it. Jack, who has a question, is a finding going to be different with bigger or smaller liquidity pool size?
I'm not sure. I mean, in our model, like liquidity pool size is endogenous variable. So if you're asking, as a result of the different parameter values, liquidity pools will be different and traders' behavior will be different, then the answer is yes. And also, if you think about some exogenous, I don't know what would be the exogenous reasons, but if there's some exogenous reasons for DX liquidity variations, then also the answer is yes. Yeah, it depends. It's going to change the traders' differentiation with the platform decision and affect the CX.